Good morning, ladies and gentlemen. May I have your attention, please? Thank you. I went ahead and duplicated our page so we have a little bit more room to work. Recall that we can solve logarithmic equations in general, right, by rewriting an exponential form if there's a single log. If there's multiple logs, then we'll have an opportunity to utilize our log props, right, whether it's one-to-one property to rewrite as input equals input and drop the log, or if it's to condense and then finally rewrite an exponential form the way that we did numbers 1, 2, 3, and so on and so forth. And so we'll go ahead and get started on our Bellwork in just a sec. So what's the invisible base? What's the invisible base on natural log, right? What's the invisible base on natural log? Braden?
10.
On natural log, Ellen?
That would be E.
Absolutely. And so when we're asking ourselves an exponential question, right, an exponent question, because a logarithm is just an exponent, we say e to the what exponent equals my input e. Well, e to the first power equals e, and so x must equal 1 for that first one. Raise your hand if you had 1 already. So ln of e is just 1. Easy cheesy. Nice job. Already here, so it looks like we did something. There we go. And now I have a single log. It's already solved for. No coefficient outside. So I'm ready to exponentiate, that is, rewrite an exponential form. Go ahead and tell the class what will that look like as a power statement. Base to the exponent equals input. So what will number 2 look like when I rewrite an exponential form? Aaron?
X squared equals x plus 1.
Awesome, thank you. Now depending upon where x is, we'll use a different series of inverse operations to solve. It looks to me like 9 must equal x plus 1. Therefore, x must equal 8. So let's check, and survey says, yes, we're 2 for 2, so I'm feeling pretty good about that. We'll go ahead and box these bad boys so that we're PDF-able. Again, power statement, be ready to share, base to the exponent equals input. What will that look like? Marina?
X to the equals 3.
Absolutely, thank you. So we rewrite base to the exponent equals input. Nice job. And now depending upon where x is, we'll do different stuff. If I wanted to solve this power equation, because x is in the base, I'll simply raise both sides to the reciprocal exponent. That is, to undo a 1/2 power. To undo a 1/2 power, I can square it. You can also solve through inspection using your half sheet. You know that the 1/2 exponent refers to a square root, right? A square root. And so the square root of what equals 3, right? Well, 9. And so either way, you can solve through inspection, or you can solve by squaring both sides to undo the exponent. I'll go ahead and write the step, though you could solve for through inspection, and that's fine with me as well. So in either case, x equals 9, and we'll box it. Great. Go ahead and share the power statement for number 4 then. Be ready. What would that look like as a power statement? Caitlin T?
4 equals 16.
Good. Thank you. So we need to make 4, right? We need to take 4 and raise it to some exponent such the result is 1/16. Well, in order to make 4 into a fraction, we need what kind of exponent? We need a negative exponent. A negative exponent will make a reciprocal of my base and then raise it to the 1/2 power. And so it looks like we need to put it all together and get negative to make the fraction and then squared to get to 16. It looks like x equals -2 is my best guess, and survey says that is correct. So we get x equals -2. Go ahead and raise your hand at this time if you had -2 for number 4. That's great work. It's trickier when there's the reciprocal. Good job. Now, base k to the exponent equals k to the 5th is how we rewrite number 5 in exponential form. And notice how k to the blank equals k to the 5th. We have no choice but for x to equal 5. And so x equals 5 for number 5. Number 6, go ahead and tell the class what the invisible base on a common log, an LOG log is. So what's the invisible base on an LOG log? Right, what's that? Margot? 10, absolutely. Thank you. And so we could rewrite this in power form. What would this then look like as a power? Logan? Absolutely. Thank you. And that's right off my half sheet. So it looks like x equals 1,000. See what it says. We're killing it today. As a power, go ahead and share. Get ready. Luke?
3 to the -2.
Nice Nice job. We can evaluate this by taking the reciprocal of my base 3 and squaring it. So it looks like if 3 to the negative 2 equals x, then x must equal 1 over 3 to the positive 2. That's 1 over 3 squared, and that's 1/9. So 1/9 would be the result for number 7. Okay, now we finally get to the new stuff. And so up until now, we've simply rewritten exponential form and used our knowledge of properties and exponents and our half sheet to go ahead and solve exactly. Now we're running into a situation where we have multiple logarithms. And so this is when we're going to be using our log properties we developed last class. Recall that we can condense a sum or difference of logs into a log of a single input, right, by using our properties. If we're going to do a sum of individual logs, we can write that as a log of a product. And so let's go ahead and rewrite that left-hand side. Let's go ahead and rewrite that left-hand side as a single log base x of, and it looks like 2 times 32 would give me an input of 64. Remember, when we multiply powers, we add exponents. So if we add logs, it must be the log of a product. That's multiplication. 2 times 32 is 64 equals 3. And now we're ready to exponentiate. And so we'll go ahead and rewrite the power statement now. I'm going to move this over so we've got a little room. I'm going to put that right underneath there. So power statement now would be x to the third equals 64. If x cubed equals 64, we can undo by taking a cube root or solve through inspection on our half sheet. X must equal 4. And our pop-up shape says 4 as well. So I'm feeling pretty good about ourselves. Nice. Number 9 is not ready to condense as is. How come? Well, we have a coefficient other than 1 multiplying that first log and the second log. And so we're not ready to condense into a single log until we can rewrite that expression with coefficients of 1 on each logarithm. So here we go. We'll grab onto my 1/2 multiplier, guys, and we'll kick it up on top of my input. Grab onto our 2 multiplier, and we'll kick it up on top of our input as exponents. Now we can rewrite our left-hand side. We get log of 4 to the 1/2 plus log of 5 squared plus log of 2 unchanged equals x. Now that I have coefficients of one of my logarithms, I can condense to a single log, and an addition of individual logs will result in the log of a product. Yes, that's right. We're going to multiply all those inputs together and rewrite it as a single log. Let's do it. I get log of, ready? 4 to the 1/2 is, the square root of 4 is 2. 5 squared is 25, so 2 times 25 is 50, and then times 2 is 100. So I'm getting log of 100 equals x. Recall that a log, LOG log, with no base written is a common log. Its invisible base is 10. So this exponent question on the left is saying 10 to the what exponent equals 100? Well, 10 to the second power equals 100, which is why my final answer is x equals 2. And number 10, we can rewrite that in power form. It looks like number 10 could be rewritten as 2 to the 5th equals 5x minus 3. Evaluating the power on the left, 2 to the 5th yields 32 equals 5x minus 3. Adding 3 to both sides produces 35 equals 5x. Then we can finish it out with the division. My final answer would be 35 divided by 5, so I'm getting 7. I'm getting 7. What questions do you guys have about today's Bellwork? Awesome. All right, then let's go ahead and take this out of 36. So this should be out of 36 because we decided to do stamps for our activity and practice. So out of 36, please give yourself credit for those that you completed from the book assignments. Divide, enter, multiply by 4. We're not going to turn in your solving exponential equations practice. I want you to keep that, right? We did it for stamps so that you wouldn't be passing it in. That way you can keep it to review from. Several of your test questions are going to look exactly like that solving exponential equations practice. So it would be a great idea to go back and do that. And I've left the answer keys posted on the side whiteboards for you to continue to check. Box your infinite campus score, nice and big, round fingers halfway 0 to 4. Nobody should have a 5 because this assignment did not involve reading questions. I'm going to pause the recording while we check our answers. Okay, ladies and gentlemen, and so let's go ahead and remind ourselves about our properties involving logarithms. Perhaps the most important in terms of solving exponential equations, like on your practice last class where you got stamps at number 5 and number 11, is the log of a power property. That is, the log of a to the x, a power, can be rewritten as the exponent times the log of the base. And so I can grab onto this exponent, x, and bring it on down front as a constant multiplier. And so that will allow us now to solve for variable expressions that were currently tied up in the exponent by getting them down the ground floor, and then we can solve through division. So everybody, let's label that log of a power property. That's log of a power property. For our second star, we have a sum of individual logs. And so the sum of individual logs can be rewritten as the log of a product. Remember, when we multiply powers, right, we added exponents. And if a logarithm is just an exponent, then it makes sense that the addition, the sum of two logarithms, could be rewritten as the log of a product. And so once again, this is called log of a product. Think about how I would write that input there that we left blank. So who's willing to share my input? How could I write that with letters? What would that look like? Mark?
AB.
AB, good. Log of A plus log of B can be rewritten as a single log of A times B. Good job. And a difference of individual logs. Remember, subtraction refers to a difference. So a difference of individual logs comes from our exponent property. When we took a quotient of individual powers, we could subtract exponents. If a logarithm is an exponent, then a subtraction of logarithms must be able to be rewritten as a log of a quotient. Bless you, that's division. So that would be log of a quotient. And let's go ahead and think about how we could write that input with letters. I'm ready to share when I call it. What would that look like inside? What would that look like inside? Carson?
A over B.
A over B. Good job. Quotient of inputs. First input over second input. Nice job. We're going to utilize these now to rewrite. So with your partner, you're going to go ahead and draw a line to connect the left-hand side log statement with the right-hand side that is a single log. I'm going to go ahead and give you guys about a minute and a half to do this, right? And then don't be surprised if you're asked to share. So go ahead and talk, right? Decide with your partner which of these logarithmic statements match, and then draw a line connecting them. Okay, get ready to share. We've got some good stuff. So not all the right-hand side got used. If you used all the right-hand side, then you made a mistake somewhere. Not all the right-hand side got used, and we've got a double upper. So we've got a double upper, one gets used twice. Let's go ahead and share then. Log 2 plus log 3, that would be log of a single number. Go ahead and share what you and your partner had for that. So what did you guys have? Heather and Adam? Log of 6 is correct. Raise your hand if you also had log of 6. Log of 6. Good, thanks guys. Now second one, log of 8 plus log of 4, then what's that going to be equivalent to? Dakota and Will? Log of 32. Raise your hand if you had log of 32 for the second one. Log of 32. Woohoo! Good job. We multiply inputs when we add individual logs. 2 log 3 could be written as log of a single number. Go ahead and share what you and your partner had for that. So 2 log 3 can be rewritten as Tyler and Olivia.
Log of 9.
Log of 9. Survey says you are correct. Raise your hand if you have log of 9 for 2 log 3. Good job. We can grab that 2 and we can kick it up on top of my input as an exponent. So 3 squared, that's the 9. Good job. Log of 8 minus log of 4. What is that equivalent to? So log of 8 minus log of 4, what's that equivalent to? Katie and Caitlin?
Log of 2.
Log of 2, because we divide inputs. First divided by second. Raise your hand if you had that equivalent to log of 2. Log of 2, good job. Log of 8 plus log of 1. Log of 8 plus log of 1. What's that going to be, Logan and Ben?
That would also be log of 8.
That's also log of 8, right? That's log of 8 because input 8, right, times input 1 is still just 8. Nice job. And 3 log 2. 3 log 2, what's that going to be? What's 3 log 2 going to be? Jackson and Olivia?
It would be log 8.
Log 8 also. Way to go, because that would be log of 2 to the 3rd power. Nice job. Way to go, you guys. What questions do you have about our matching? Then we're going to go ahead and begin now with our logarithmic equations activity. Okay, so we're going to be working together in our small cooperative learning groups, and we have several stamped eligible items. We've got 6F, 9F, 10F, 13, and 18. I've posted my worked out solutions on the rear whiteboard. So you'll notice that we've got two separate answer keys out there. The first is your solving exponential equations practice from last class. And then today's is the solving logarithmic equations. The solving logarithmic equations. Go ahead and do a quick circle around each of the stamped eligible items. I'm going to pause the recording now, and then we're going to come back together and summarize our findings. We'll resume the recording and go ahead and take a look then at our strategies. And so, as a result of this activity, we should be able to break up our logarithmic and exponential equations into several different types. Firstly, if we have an exponential equation where my output is not a perfect power of my base, then only one of these strategies, either blue, red, or purple, is going to be appropriate. So everybody go ahead and take a look. In order to solve 2 to the x equals 5, only one of these strategies, the blue, rewrite using log props. The red, use 1-to-1 property. Or the purple, take log of both sides, is going to be the proper strategy. So what would we have to do in order to solve that first one? 2 to the x equals 5. All right, what would we have to do to that? Adam?
Going to do the blue.
How would I get that variable down out of the exponent? What would I have to do to allow me to get that variable down to the exponent?
Take the log.
Absolutely. And so in order to solve an exponential where my output is a non-perfect power of the base, we're going to take the log of both sides and then bring down that exponent as a multiplier in front. Good. If we have logs, multiple logs, but just on one side of the equation sign, typically we'll rewrite, but then rewrite in exponential form to continue. And so the second one is the blue, right? We're going to go ahead and condense that using log props and then exponentiate. Versus if we have logs on both sides, that's when we get to use the easy one. If we have logs on both sides, that's when we'll use the 1-to-1 property. So once again, exponential equation, output's a non-perfect power of the base. We've got to take the log of both sides so we can bring down the variable out of the exponent. Multiple logs, but only on one side, we'll rewrite in exponential form. Logs on both sides, we'll condense and then use 1-to-1 property. Let's try it some more. Logs on one side or both sides? Logs on both sides. So go ahead and match now with your partner which our strategy is going to work now that we did one. Be ready to share.
1-to-1.
Okay, what strategy for the first one then? For the first one, Will and Dakota? The which one? Absolutely, the blue one. This is logs on both sides, so we're going to go ahead and condense. and then use the one-to-one property, log equals log, and drop the logs. Good job. Logs on the single side, we can then rewrite in exponential form. So the second one is going to be rewrite using log props in green, the bottom, which means that my exponential, or my output, is non-perfect power of the base 5. That means we're going to take the log of both sides and rewrite. Raise your hand if you had this matching already. So who had this already? Way to go. Let's do it. So here we've got a short amount of time left, but we'll go ahead and do it. Recall that we can take the log of both sides, and it doesn't matter which log we choose, log common log or natural log ln, both are on our calculator. So we'll do that. That'll enable us to bring down that exponent as a multiplier in front. And now we can solve through the inverse operation division, where before we had our x up in the exponent, now we can solve through division. So my final answer will be given by x equals exactly ln 5 over ln 2. And we could certainly get a decimal approximation for that, just like you guys did well in your activity. In the interest of time, I'm just going to box that and continue on. Multiple logs on one side. What was our strategy? Condense and rewrite as a single log, and then exponentiate. So we'll go ahead and rewrite using log properties. Here we go. I know that the sum of individual logs can be rewritten as a single log of a product. So log of 5x equals 2. Now we're ready to do an exponential form. The invisible base on a common log, log, is 10. So 10 to the second equals input. That means 100 equals 5x. And we can finish out through division. So my final answer for the second one, number 2, will be x equals 20. What questions do you have on 1 and 2? Great. Then 3, logs on one side or logs on both sides? Logs on both sides. So this is the easiest one. Rewrite as log equals log, and then drop the logs in accordance with the one-to-one property. We have no choice but for x plus 5 to equal 2. Then we can solve through subtraction. It looks like x equals negative 3. And in 4, no logarithms at all. So I'm not going to be condensing logarithms here or using one-to-one property. Instead, we've got to isolate that exponential through addition or subtraction, multiplication or division, and then take the log of both sides to get that variable out of the exponent. Let's do it. Well, best first step. Plus 12 plus 12. Next step, divide both sides by 3 to isolate the exponential. And then now we've got an exponential equation where my output is a non-perfect power of the base. What do? There's my strategy. Take the log of both sides. That's what we learned. You can do the natural log or the log log. Either one is correct. That allows us to bring my exponent down in front with a constant multiplier. X times ln 4 is equal to ln 21. And now I can solve through division. It looks like x equals exactly ln 21 over ln 4. Again, we could get a decimal approximation for that, but in the interest of time, we'll go ahead and box it and continue on. Okay, so what strategy is used to get a variable down out of the exponent in order to solve? What do we do to get a variable down out of the exponent in order to solve? What do we do to both sides? Jackson? Absolutely. We take the log of both sides. That's a new strategy. Awesome. Go ahead and solve those two. Go ahead and solve these two and be ready to share. Number 2, looks almost exactly like one on your final exam. Almost exactly like one on your final exam. All right, what did you do to number 2 to kick the party off? Cody, what did you do first to solve number 2?
I did the log.
Awesome, and since we just, awesome, instead we just did ln on the previous slide, I'm going to do log log if that's okay with you, Cody. I'm going to do log of 3 to the r equals log of 26. Perfect, now I can bring that r down in front. R times log of 3 equals log of 26. And we can finish out through division. R must equal exactly log of 26 over log of 3. Nice job. 1 to go. In this case, I've got a single log, right? Log on one side, so I'll go ahead and rewrite in exponential form. I'll go ahead and rewrite in exponential form to finish this out. So base 5 to the x minus 3 equals 80. And now we've got to do the log. Since we just did log log, I'll do ln. We'll bring down, just make sure that you bring down quantity, right? Bring down quantity x minus 3 in front. And I'm going to show that with parentheses. And then division, we'll get the variable expression x minus 3 alone. And finally, we can finish it out through addition, right? In order to finish it out, we have to now add 3 to both sides. So my final answer would be given by exactly x equals ln of 80 over ln of 5, and then plus 3 after the fact. And this looks similar to several that you guys had in your logarithmic equations activity. What questions do you have about our closure today? Great. The next time we'll be calling for a stamp count before your test. So I just wanted to share this with you guys. Activity stamps included 2 from your solving exponential equations practice, and I'll still issue these stamps at Bellwork next time, so everybody gets full credit for completing your solving logarithmic equations. I'll go ahead and save the recording at this time. Nice job today.